Okay, so this one, as I mentioned to you, that the chapter 5 was easier to present. And so I decided to put the finance chapter first, even though it's an OM class, sort of. Okay, so now we're going to do the application to production and inventory problems. I do want to mention that applications of optimal control to production has gone back quite a long period of time. But anyway, the application of optimization methods to production and inventory problems goes all the way back to EOQ problem of Ford W. Harris, 1913. And we have a dynamic version of lot-size model, which used dynamic programming by Wagner-Witten. As we know, calculus of variation was a precursor to optimal control theory. And 4 people go by the name of Holt, Modigliani, Muth, and Simon. They worked on a production planning problem. It's called now the HMMS model. This is not the right ear. Definitely not right ear. And they use a calculus of areas to solve it. We're gonna fix this with this ear. Modigliani, Holt, Modigliani, Muth, and Simon. 2 of those guys received Nobel Prize in economics. The Modigliani and Simon are the Nobel laureates. But they were working on an optimal calculus of variation problem to apply to a production planning problem. That became quite a famous model. What they did was they took the data from a Pittsburgh paint factory. They were all professors at Carnegie Mellon at the time, before my time, and they took the data from Pittsburgh paint factory and then tried to forecast using that data. They tried to show that by using their model, they can substantially increase the profit of the factory. And they wrote a book actually also on that topic. Thompson Sethi took this particular problem and tried to apply control theory instead of calculus of variations, and also developed some other ideas of what is called the turnpikes. And that was published in Management Science in 1980, and I will present that paper as the first paper in this topic, on this chapter. And the second chapter, the second topic on this in this chapter is a retreading model of Ejiri and Thompson. He was a professor of accounting at Carnegie Mellon, and Thompson was my advisor. Both of them are no more, but they developed this paper in 1970 and published in Accounting Review. That's an accounting journal. But this model is the one that I took to illustrate the pure state constraints, and also showed you something, ideas of horizons. What I'm presenting here were never published except in the book. I didn't try to publish that in any of the journals. But these are some of the very nice applications of state constraint problems, and also has got some other ideas. Okay. So what is the idea behind a production inventory problem? Well, the idea is that there is a demand which varies over time, and we can produce, but if we produce exactly according to the demand, then changing production and all that may not be all that interesting and could be expensive. So you want some sort of smoothing. But then what happens is that if you want to do that, then in the period of low demand, you can produce a little bit higher amount, in which case you need to store. So there's an inventory cost of storing the product. And then that stored product can be used when the demand is high. So that's sort of what is going on here. So this is a production planning problem, production inventory problem, where you try to optimize the production in order to meet a time-dependent demand. And you do have a warehouse where you can store inventory at some cost. The idea behind this particular model is that there are excuse me, if you think of production smoothing, one of the way you do it is to include the cost of changing the production. And so when you have a time-dependent demand, and if you follow the demand according to the production, then the production is going to change according to demand, and the rate of change of production will be expensive because we have a cost of changing production. So that's one way to do smoothing. What Holt, Modigliani, Muth, and Simon did is a different way of smoothing production. They decided that there is some kind of a good level of production, which is a factory optimal. That means higher than that would be a little bit more expensive because cost of production is kind of convex. So you want to produce more than that is going to be more expensive because whatever the reason, that one of the reason could be that you have to hire labor, you have to pay them time and a half. The cost of energy may be more expensive. If you do underproduction, that can also be expensive because you have to send some people home with pay. And so all in all, one could say that there is a goal level of production, which is kind of factory optimal. Similarly, there could be an inventory level, which is a factory or warehouse optimal. That means that if you have too little inventory, and then you have an opportunity cost which is not being used. If you have too much inventory, that there will be a spoilage, and also if you have too much inventory, you may have to find an extra space somewhere else beyond the warehouse. So altogether, one could think of a goal level or a factory optimal level of inventory. Those are called I hat and P hat. Okay. What Holt, Modigliani, Muth, and Salmon said that if you deviate from I hat and if you deviate from P hat, it's going to be costly. Okay, so that's the idea here. You don't want to deviate from these two levels, and if you deviate, of course, there will be some cost, but we're going to minimize. We're going to try to minimize the cost of everything. So the IT is the inventory level at time t. PT is the production rate at time t. ST is the demand, which changes over time. T assume is the length of the planning period. We're going to assume it to be fixed right now. I0 is the initial inventory level, which can be 0, but we can assume in general I0. We allow shortage, so we allow negative inventory levels. That means we allow backlog. H is the inventory holding coefficient. C is the production cost coefficient. We'll briefly tell you what that means. And rho is the constant negative production discount rate. Since it's a finite horizon, we can assume rho to be bigger than equal to 0. If t equal to infinity, then we would like this rho to be strictly bigger than 0. So clearly, as we have in chapter 1, this was one of our examples in chapter 1, I dot, which is the rate of change of inventory, it increases as production and it decreases the demand. So it's PT minus ST. We have a beginning inventory I0. So we have a stock flow differential equation, which is our state equation for this particular problem. What Holt, Modigliani, and Muth, Salmon says that if I produce inventory that deviates from I hat, it's going to cost me this amount. You see, this is a convex cost, quadratic, and it is 0 at I hat. Above I hat is going to cost you, below I hat it's going to cost you, but the amount it costs you is h divided by 2. That could be, for particular purposes, I could assume to be just one or one half. And the reason they divide by two is because when you take a derivative of these two, they want two and two to cancel out, so they have less fractions. But basically, there is a constant that could be one, or that constant could be some number. Okay. And then similarly, there's another constant which goes with the production, and the production deviation will be expensive also according to this quadratic function. And there's a discount rate. So you discount by this discount factor and integrate, and you want to minimize this. This is the cost. Okay. So you could think of that could be a penalty of producing more or less than the best level for the factory or the inventory, and that should be the production, which is the producing bigger or above, and there's a penalty of doing so. That's in keeping with Hall, Modigliani, Muth, and Simon. So I'm going to maximize this. So I'm going to put a minus sign in there. So we have a maximization problem. And we then develop the Hamiltonian. The Hamiltonian is lambda times the state equation minus the integrand of the objective function. We are assuming, as you can see, we are assuming no salvage value right now. Okay, so that's our problem right now. And we apply the Pontiac's maximum principle. We take the derivative with respect to P, so that gives you a condition for optimization at any given point in time. And so the optimal production rate is given by some ideal level that we already know, plus lambda t divided by c. Lambda t is the value of the adjoint variable. Now notice that we cannot really have a negative production. Negative production is like throwing away goods, called disposal. You can allow it. Mathematically, it is not a problem. But realistically, it is generally not assumed that we have a negative production. Okay. So then if you don't have a negative production, then the first order condition, along with that constraint that P has to be bigger than or equal to 0, I can put P star T equal to max of that quantity and 0. Okay, so that's our first order condition with the constraint that the P is going to be non-negative. Let's continue. I dot, if I can tell you that there's a I is P minus S, and I already know what P is in this term. So let me do the following. We are going to assume that for the time being, our lambda is such that this quantity here is always going to be bigger than 0. Okay? And notice why we can assume that. So see, here's what's going on. If my initial inventory is not very large, which means that there is no great penalty here, then I have a feeling that the production will be not outrageously negative or low. And so we can only encounter this negative production if I0 is too large in the beginning. Okay. Once we deal with that, this model will automatically come to a point where it will not allow you to have negative production. So we could sort of assume for the time being, to simplify the problem, that this I0 is not very large. So it's sufficiently small, let's put it this way. Okay. Or not too large, like this way. If that's the case, then I can substitute for P in my I dot equation, and I can get I dot equal to this. The adjoint variable, on the other hand, is lambda dot is rho lambda minus delta H delta I, which can be given like this, and lambda t equal to 0 because they have no salvage value. Now, when there is no constraint of this kind, and when the equation of state is linear, and the objective function is quadratic. This is called a linear quadratic problem. I have a whole section in appendix of how to solve a linear quadratic problem in closed form. That particular section allows you to have vector here and allow you to have a vector state variable, allow to have a vector control variable, and allow even to have stochastic noises that you can put into this inventory equation. So that is all in Appendix D. It is a main topic in electrical engineering because linear quadratic problems are some of the ones that can be solved in closed form. And there are many times problems that are not linear quadratic gets approximated by linear quadratic problems because that is the only game in town in some sense. So we're going to basically remove this constraint, makes whatever assumption we need to make so that we don't encounter this constraint. And we would use the linear quadratic methodology for solving this problem. Towards the end of this particular problem analysis, we will show you how we can deal with if that's a constraint. And that would mean that we don't have a linear quadratic problem anymore. It will be a little bit more complicated, but we can tell you that there is a way to deal with it. So while I'm making an assumption to simplify things, I'm not telling you that I cannot solve the problem if I take that constraint into account. I can. So we will worry about that later. So how do we go about solving a linear quadratic problem? Well, there are different ways of doing it, but here's one. There's another way we will show a little bit later, which is coming from, again, the methodology applied to another way to a linear quadratic problem, and that one will be by a paper that was done by Alab and Susan, and I covered that as well in this third edition of the book. Wasn't done in the second edition. Okay, so the one way to solve is to eliminate lambda from our state equation. Okay, one way to do is to take the derivative of this guy. So I take another derivative, I double dot. That will give me a lambda dot. I can substitute for this lambda dot in terms of lambda. And then I can substitute the lambda. I can substitute the lambda from here in terms of p. So I have only I and a p. Okay, that's the goal here. So take I dot, lambda dot, take the derivative, take the derivative, substitute for lambda dot. I now have an equation, I double dot equal to rho I dot p dot dot dot. Notice this is a second order linear differential equation. That one. And h divided by c, I can assume that I can define that to be alpha. So by writing this equation, I can rewrite this equation this way. This is a second order linear differential equation. And notice right hand side is just a function of time. I know I hat, which is a constant. I know p hat, which is a constant. I know s, which is a function of time. It's a given demand. And I know s dot because I can take the derivative of that. And that will be also given of time. I'm going to assume that this s is differentiable. That is not a big problem here. And so we can write this as a second order differential equation. In Appendix A, I also give you the methodology of solving the second order differential equation. The way you solve it is you take an auxiliary equation. Wherever you have I double dot, you put m squared. Wherever you have I dot, you could put m. And then wherever you have I, you put a constant. So this left-hand side, if you take that, and if you take the auxiliary equation, then this left-hand side is given by this equal to 0. This is called a forcing function. We'll talk about that later. When you have this particular system, you can solve that equation as a quadratic algebraic equation, and it's got two roots. Okay. One root is negative. As you can see, this is rho minus rho squared plus alpha squared. So this is bigger than rho, so that's negative. This is positive. So we have a negative root and a positive root. It turns out that if you have this equation and that auxiliary equation and those roots, then a general solution of this equation can be written as follows. IT is some constant times e to the m1t plus another constant times e to the m2t, and then there is something called a particular integral, which is the particular integral of 6.9, and it comes about because of this right hand side. Different right hand side will give you a different particular integral, and I have a table in appendix that gives you a particular integral of some of the stuff that we might be using in the book, or at least in this chapter, and some more. Notice that particular integral comes because of this, and there's a special case of particular integral that does not include term which have e to the m1t and e to the m2t. The reason is if you have some e to the m1t, e to the m1t, they can be brought into this one, and all it means is this constant. In the end, remember, we have two equations to begin with, I dot and lambda dot. We have two conditions which we need to solve these two equations. Now we have a second order linear differential equation that needs two constants, because there are two constants here, a1 and a2, a1 and a2. These are constants of integration. These constants will now be determined by these two conditions that we have. So basically we have turned this 2-point boundary value problem into a second order differential equation with two unknowns, which will again would require those boundary conditions for us to solve them. So what I'm saying is that if you put some of the terms like that in a particular integral, it is not necessary to include them because these are constants anyway that we want to determine. So we can do a special particular integral, and the table in appendix is given for special particular integrals. Okay. Once I have this solution, so I have a solution now. I now need to determine a1 and a2. Okay, because I have this, I have m1, I have m2. Only thing I don't have is a1 and a2. I have initial condition, so I need a1 and a2. Okay. Well, I know that IT. So listen here. Lambda dot can be written in terms of I. Now I already know I is given here, this one. So I can substitute that I and I can get a lambda t. Okay, and I can solve. So I can get lambda, and for lambda is again a very simple equation. So we can solve that equation and we get a solution of lambda, and I have a lambda t equal to 0. So you can see now I put I0 equal to I0 and lambda t equal to 0. I got two equations and I have two unknowns, A1 and A2. So by using these two conditions, I can now find, by solving the two algebraic equations, A1 and A2. And that's very easy to do. You just put 0 and you have this will become, when you put 0, this will become A1 plus A2 plus Q0. And so we can do all of that. And since we know Q2, we also know Q dot. There'll be examples soon, so don't. So I want to solve A1 and A2, but A1 and A2 are rather complicated expressions, even though they're two algebraic equations, easy to solve, but the solution is kind of messy. So in order to avoid the messy solution, I want to put B1 equal to I0 minus Q0 and a B2 to B, because I can collect terms when I get a big long solution. On a big long solution, I collect terms, and I can kind of rewrite the solution A1 and A2 as follows. This is a solution of the two algebraic equation that you get by putting these two conditions. Okay. And so there we have the solution. And what remember the Q is coming in there, but the Q is in B1. So the Q is sitting here, but it's part of B1 and B2. So this is where um, Thompson has a working paper at the time when I was a student, and that working paper was being written. We didn't finish it, so he gave it to me, and he says, "Okay, here's what I've done so far. You want to go and do something after this." So I said, "Okay, go ahead, give it to me." So this is then, and this is one paper where you can see that, generally speaking, I go by alphabetical order, but but in this particular case, I think it's fair that Thompson gave me the working draft paper of some sort, and so he asked me to do something. So this is the Thompson-Sethi paper. So here's where you go. Suppose M1 is negative. So what we're trying to do now, so if you only stop here, you have solved the whole Modigliani-Muth-Simon problem. Okay, so if you don't want to go any further, we are done. It's just using maximum principle to solve the same problem that the HMMS solve using calculus of variations. Okay, but we want to go further. After all, we're trying to publish in management science. We want to go further to see what we can do beyond this. So here's the next part of it. We're trying to find out some sort of equilibrium. We try to find out if T is very large, would there be some sort of a stationary equilibrium in this particular problem? And in economics, such a solution is called a turnpike. Okay, I'm going to tell you a little bit more about why it is called turnpike in economic theory, but this is kind of a turnpike analysis of what economics people call turnpike paths, or growth economics. There is something saying the growth follows a turnpike. So let's see what's going on here. If M1 is negative, M2 is positive, and if T is sufficiently large, then this quantity can be ignored. This is going to be very, very small. Okay, so if I ignore this quantity, here's what happens. Suppose I make this to 0. So this becomes 0, this becomes 0, and I am left with this. Minus minus cancels out, M2 cancels out, this exponential factor cancels out. I have A1 is approximately equal to B1. So I have A1 approximately equal to B1. Okay. Again, this one goes out. This one goes out. So these are 0, 0. That goes out. And M1T and M1T, that power cancels out. Okay. So I'm left with B2 divided by M2 e to the M1T. So I'm left with this guy. Or minus comes because there is a M2, it is in the denominator. So when I bring it in the top, it becomes e to the minus M2T. Okay, let's now take this and go to the next table. So we have a solution. We put A1 and A2 back into this, but the approximate value of A1 and A2, if you think about it. If I put all of those in there, I get the following formula. That's the I star T. I also know lambda, so I can do lambda. I also know P star, so I can do P star. So what we're saying now is that somehow or the other, if T is very large, then we expect this quantity to kind of go to 0. Okay, this T is large, so and this M2 is positive, so M2 times minus T will become, will be very small, at least in the beginning. But but as small t goes to whatever is small t is, this t goes to infinity, we can kill this term. Okay. So this is what is called the Turnpike expression. That means eventually, as time goes to infinity, we will approach the solution to this value. So I star t will be q of t in some sense. Because as t becomes bigger and bigger, this quantity becomes smaller and smaller, and this quantity is approaching 0. So asymptotically, I star is approaching q in some way. So if b1 was 0, then I0 is q0. That means if remember, if I0 equal to q0, then b1 will be 0. So if I have an initial inventory which is exactly equal to q0, then I will stay at q, because I begin with q0 and I will just stay at q. Same way, b2 equal to 0, the ending correction will vanish at each of these formulas, and the solution will stay in Turnpike until the very end. So that's sort of the idea here. Okay, so let's see how we go about doing something more on this. If t goes to infinity, then we can remove this term, and we can write lambda t like this, and we would like our sufficiency condition, we should have this quantity equal to 0 as t goes to infinity. We can show that for that to be equal to 0, this quantity has to grow not very fast. It has to grow slower than rho. Then e to the minus rho t will kill it as t goes to infinity, and this will then become 0. We can show that for several demand forecasts S, that we can actually have a formula for QT. And generally speaking, all the formulas for QT that we know that are closed form, they are not growing as fast as rho. And so we are okay. They're not going exponentially as fast. So we are okay to say that this holds in most cases. Okay. So that's all that is here for this case. And so once you have that, we have a sufficiency of the maximum principle. And the sufficiency of the maximum principle allows us to say that this is an optimal solution. And so optimal solution is given by this. Now, we can also find what is a turnpike. Another way to, so the turnpike is I bar, P bar, Q, lambda bar, which is Q. And a P bar is Q dot by S, because these quantities are going to 0. And since also lambda, we can do something also for the lambda, which is going to the equation to lambda, and we can kind of say this goes to 0, so this is your turnpike for lambda. So I have this turnpike. So now let's take some examples. One example is that I can assume the demand to be a polynomial. And of any degree polynomial, you can actually write this to be a polynomial degree of 2p. And then for that, Zwillinger tell you what the particular integral is. So we have a particular, special particular integral given by this, where s of 2p plus 1 means 2p plus 1th derivative of s. Sk denotes the kth time derivative of this st. So that means first derivative, third derivative, 2p minus 1 derivative, okay? So there we go. If you have a sinusoidal demand, we have a particular integral of this kind. By the way, there's a table in appendix that gives you all of these formulas. Again, we're not teaching differential equations here, so we're just going to use formulas that are available to us. But as I mentioned to you in the beginning, you should know what a differential equation mean in principle. What is a differential equation? What does it mean? How to formulate it? And what does its solution mean? Okay, whenever the solution is given to us. So here's an example now. We have a cubic polynomial as our demand. We have a goal level 30. I at goal level is 15. Time is 8. We assume rho equal to 0 for simplification. It's a finite horizon problem. We assume h of c equal to 1 to not have too many variables or too many coefficients, which are only make it messy. Alpha equal to 1. M1 is minus 1. M2 equal to plus 1 for this problem. And we have a special integral for this problem to be given by using this formula here. We can give the special integral to be given by this polynomial and q dot t given by this polynomial. Once we have that, we have I star and a P star. These are the optimal solution of the problem. You notice that if I0 is P3, B1 becomes 0, and this term disappears. Again, this term disappears, so when I0 equal to P53, this disappears. If t equal to infinity, capital T equal to infinity, that disappears. So you can see if we begin with 53, we will stay on Turnpike forever. We are on Turnpike right from the beginning. So if I give you inventory of 10 and I graph these formulas, you see the following thing happens. The demand is given by this sinusoidal curve, like that. Not sinusoidal. It actually is a demand is given by a polynomial, which is 0 here and a 0 here. So since I have a very low demand, I have to produce, no, which I have very high demand and very low inventory, I have to produce some quantity in order to catch up with this demand. So you can see that the demand is ST, and I'm going to start producing at 49 because I have very little inventory. I want to meet some of the demand so I'm not too much backlogged. And so I'm going to produce at 49, and then this quantity is the way the inventory goes. And you can see the inventory eventually at 8, it's exactly 29. Okay. Now I start with the inventory of 50, which is a large inventory. The demand in the beginning is still 30. So now I can start with a production which is small. So I can start with a production of 10 to begin with, and then production will increase like this. But you can see the inventory goes from 50 all the way and eventually settles at 29 at 8. The third example, I have a 30. So I'm right now at 30. And so as you can see, production is now also more or less in some way close to demand. And the inventory now has this particular profile and eventually goes to 29. You can see that regardless of the inventory that I have, this solution seems to going all the way to 29. And if I had a bigger horizon, you can see that after this, the solution has reached some kind of a turnpike. Because every solution is going there, and then from this point on, it's kind of follow a turnpike if there was a bigger than 8 periods. But that's you're not working there on right now, but it sort of give you some idea of what's going on. Notice I did not do this calculation. I did it like a few minutes ago before the class. If I had I0 equal to 53, then this becomes 0. Okay, so I star t becomes qt minus that, and if at capital T, it becomes actually q of t minus 24. It turns out that if I begin with 53, then Q of t, capital T, in 8 period will again be 53. So the Q of t will be again 53, and 53 minus 24 is again 29. So even if I begin at 53, I will also end up at 29. But I will be at Qt, I start, it will be Qt minus 24. Okay, so it is kind of approaching Qt, but it will only be on the turnpike, which is exactly Qt, if capital T is infinity. Now, I don't have that problem solution for this because t equal to infinity, usually you cannot have this kind of demand. This kind of demand is not good for t equal to infinity. Just think about here. If you like this kind of demand, you see this demand is going up like crazy all the way, like infinity cube, if you think about it. It's very large numbers are going there. Okay, so this is a finite horizon example. If you want to go to infinite horizon example, you're going to take one of these kind of guys as a demand and then run an exercise through again. So if if you go to forecasting course, in the forecasting course, you may learn different kind of demand forecasts. And this is a very popular demand forecast. It says the demand is constant plus some trend. The trend is B times T. So there's a trend in the demand. That is a growth in demand at T. Plus there is a seasonal factor, which gives by this seasonal factor, which is given by the sinusoidal function. And then there is some trend in the seasonal factor as well, which is given by this particular T. So you have the sinusoidal function and this and this. So this, and for that, even for this complicated formula, we have a particular integral given by that. We have two things to finish on this particular problem, which are, again, the problem is simple. The problem is designed to teach you some optimal control aspects. And so there are two more things that I need to talk about on this one, and let's just do that. One is Holt, Modigliani, Muth, Simon. Their article was called Linear Decision Rule. They said that the Pittsburgh factory can apply a linear decision rule, which means that the production is linear function of your inventory. So whatever inventory you observe, you apply that function and you have an optimal production rate. But now using optimal control theory, Ben Susan writes a paper which is like this. Because of the two-point boundary value problem, it is known, again in the theory of differential equation, that lambda t can be written as follows, where the psi t and s t are to be determined functions and they are continuously differentiable. So what we are trying to do is finding an equation in a variable which is kind of derived from lambda and I. So now we differentiate 6.32 and we substitute for I dot and lambda dot. And we know these equations, these are the state equation and adjoint equation that we already know. We have also rho equal to 0. In this case, let's assume rho equal to 0 for simplicity. Then we have this equation in S dot and psi dot. Notice that this equation must hold for any value of initial inventory. If it holds for any value of initial inventory, then this quantity, which is the multiple of I, has to be equal to 0. So that equal to 0 gives us one differential equation. And because this has to be 0 and that quantity has to be 0, because that is equal to 0. If this is 0, then the remaining part is this equation. So we have a differential equation of psi dot. So by using this formula, we are converting lambda and I two differential equation into a differential equation S dot and psi dot. And by using the conditional lambda t0, we can show that this function at capital T will be 0. And this is true for regardless of the value of it. So we should have S t equal to 0 and psi t equal to 0. Given these two conditions and given those two differential equations which are derived, we can solve what is called a, a, a system of equation which is called a Riccardi equation. Here the word Riccardi. And Riccardi equation is well known in linear quadratic problems, and this is the Riccardi equation, where you have S dot and on the other side there is a S squared term. And its solution is given by this formula. Once you have this formula, you can sort of see that the P star T is a linear, this is a function that we can compute, just a function of time. That's all there is to it. And here's your inventory at time t. So you can see that P star T is a linear function of inventory. This will be another time function. This is a constant. So you can see that is some, you can write P star T to be capital A of T plus B of T times I star T, where A T and a B T are time functions and given functions. So you can see it's a linear equation where the coefficients change over time. That's the Holt-Modigliani-Muth linear decision rule coming through this particular formulation. And I wanted to do this because Riccardi equation is common in linear quadratic problem. So I want to give you this little formulation by Ben-Susan that is sitting in here. The last thing I did is what I promised you. If I allow non-negative production constraint to be a real constraint, which means that I allow any initial inventory, and if I have a large enough initial inventory, then I will probably have to do something in the beginning, which means that in the beginning, that quantity, the production that I have, well, the formula is here as well. This formula was kind of production. And that formula, if that becomes negative, then I cannot use negative control. I can only use zero control. So rather than, okay, if I could dispose, I will just dispose it. So I will have a negative control. I will have a P star to be negative, and the problem is solved. The problem is solved as before, okay? If I allow negative. If I don't allow negative, then I must have P star equal to 0 whenever that formula gives me P negative, okay? So what I'm now going to solve a problem where I will do 2 or 3 things. One is I'm going to allow you to have a t equal to infinity. So we didn't do t equal to infinity so far, but we can now do t equal to infinity and give you the idea of this turnpike and equilibrium or long run equilibrium. And I'll assume rho bigger than 0. In order to make my life simple, I'm going to assume that demand is constant. Okay? And when the demand is constant, we can go we have to go back all the way to our formulation of 6.9. And let me let's save some time because these are very simple things to go and refer to. So the big idea here is that I'm now going to be interested in trying to see how I can solve the 2-point boundary value problem when I must have this constraint, which is non-negative production constraint. So for this simple problem with rho equal to bigger than 0, t equal to infinity, demand to be constant, the particular integral is given by this. You see the particular integral is also a constant. This is constant, p hat is constant, s is constant. S is a demand, which is a constant, I hat is a constant. And q dot equal to 0. So I can now write the formulas B1 and B2 that we had before. And t equal to infinity means the ending term disappears. So only we have left with the beginning term I0. And we will see that when I0 is quite large, it will ask us to have a zero production as optimal solution. Let's also define the turnpike by another way. So what we already defined the turnpike by taking the limit t equal to infinity in the solution that we have for this problem. But you can also see that in chapter 3, we have what is called optimal Lagrange stationary equilibrium, a triple or a quadruple depending on whether there's a constraint. So if there's no constraint, we will have a triple solution, which is I bar, P bar, lambda bar. And you can sort of see that that is the solution, which is also the solution that we got earlier. So we have three cases. We know that if I0 is less than Q, the inventory is very small anyway, so there is no reason for us to produce 0. That means the unconstrained production will be positive, and the solution that we obtained is good enough. It's also optimal. We will also see that only if I0 is bigger than this quantity, that formula for P star becomes negative. So once again, this condition also is okay for us to have a solution which is the unconstrained solution is also optimal solution. So only when I0 is bigger than Q minus S by M1, I will run into a condition where I must have in the beginning initial production to be 0. That means the constraint will be active. Let's now go to the picture and see what is going on here. Case 1. If I0 is less than Q, our control 6.25, we can show that this 6.25, let's go to 6.25. So this P star, we'll see that this is going to be, if you put the formula that we have for Q dot and everything, this formula will say that the P star is bigger than 0. Okay. So let's look at the picture now. So this is Q. This is our turnpike. It's a constant demand. We'll have a constant turnpike. These are the numbers for this picture. These are actual drawn picture for those numbers. So here's your turnpike. You can sort of see that if I0 is less than Q, this is Q. Here's I0. I'm producing according to our formula. This is the formula that I'm producing according to the formula. Formula gives us. So if I'm right here, then I will stay right here by producing P star equal to S. That means I have a Q here. I will just stay there, but I'm going to produce exactly S all the time. So I'm producing exactly equal to demand, so my inventory will stay exactly at Q. So Q is 7.60. My inventory will stay exactly at Q. Okay. If I0 is less than Q, then production will increase. It will be bigger than demand and keep going until the production asymptotes to S. Turns out that if you look at the formula, uh, you will see that if I0 is less than Q, I will never reach the turnpike in finite time and will continue on that. I will reach the turnpike asymptotically. Only if I have I0 equal to Q, I will be on turnpike exactly. Any other value of I0, the turnpike will be asymptotically reached, and you can sort of see that by this formula here. You see that as t goes to infinity, this goes to 0. So if I0 is equal to Q, I'm already at Q. But if I0 is different than Q, then this quantity will approach 0, but never will be 0 at a finite time. So you can see that I star t will asymptotically go to Q because this quantity is asymptotically going to 0. So that formula is plotted like this. Similarly, if I0 is between Q and this formula here, we can see that there is no reason for us to worry about the constraint on production. And once again, the production will be such, which is given by this formula, that it will actually go to approach, in inventory will approach the turnpike as time goes to infinity. Notice the following thing is important now. That Q minus S by M1 comes from the formula of P star going to 0. So if I0 is exactly at this point, Q minus SMN, then P star will actually be 0 in the beginning, and then it will start increasing. And eventually will go as a turnpike. So you can see that up to I0 equal to this number, I have all the solutions. These are optimal solutions. So this is the insight that you have to have. The insight now is that I have solved the problem. This is the boundary case. Boundary case is such that P star is at the constraint only at time 0, and after that it is no longer there. So at that time it is 0, it is at the boundary. But formula, the formula, sorry, this formula, this is where that comes from. That is exactly the formula that allows us to. So if P star is this formula, this is already 0 at 0, then it's max of 0 and 0, and I'm okay. Okay, and after that it becomes bigger than 0. So the only problem that I have to deal with, if I0 is bigger than this quantity, so I0 is somewhere here, doesn't matter where it is, it's bigger than there, then that formula of P star will give me negative. So the max of negative quantity and 0 is 0. So I'm going to produce 0. So you can see P star equal to 0. So if I0 is here, this is arbitrary. It could be anywhere. All I'm saying is in the case 3, it is above this dot. Then I will produce P star equal to 0. That is in a straight line. By the way, this picture was redrawn in edition 3 because we did not had such a good job there. This is a straight line because I dot is P minus S, P is 0, so I dot is minus S. Minus S is a slope of S. S here is 6, so this is a slope of 6, and it goes all the way. Notice now, at some point, that trajectory, because I'm producing nothing, and my demand is 6, at some point, that I0 inventory will go down all the way to this dotted line. This level is exactly Q minus S divided by M1. We already solved the problem when I0 is Q minus S1, and I have a solution like that. Now when I have an I0 here and I'll apply 0, I would eventually arrive at this number of inventory quantity exactly at some time t hat. And I can easily compute the t hat. It is simply I0 minus this divided by S. That's the amount of time it will take me to deplete that much inventory so that my inventory becomes this. So at t hat, I have exactly the inventory Q minus S. Okay, so but then at t hat is just some number of some time, right? So if I begin the problem at t hat with this inventory, I will be in this case where inventory is at time 0 at this point. So what I'm trying to say is that t hat I can call this time 0. And if I call this time 0, then that solution is the solution. That would be a solution from here. I can simply shift that solution which I obtained in case 2. So in case 2, see, I obtained this solution. So you'll see a little bit later. So case 2 is this case, and I obtained the solution in case 2. I will go over this very quickly. So I actually have the solution from t hat, and I have a solution before t hat. So I have a solution. I have a solution of before t hat and after t hat. All I have to do now is to find, I also know lambda here, because lambda here is going to be the same as lambda here, except that I have to substitute t by t minus t hat. So then I will get the lambda, and I'll get the I. All of that I will get. So once I have the lambda and I here, I have the condition for lambda here. With that condition for lambda here, I can go this side. I can solve the differential equation of lambda in this interval, 0 to t hat interval, backward. And I can find the lambda there. And once I find the lambda, I have a solution. And it is intuitive to believe that that solution will satisfy the maximum principle. And you can check that out. You can verify that with that lambda, the solution satisfies the maximum principle. Okay, so now we go through. So you got the idea here. This is the picture. There is no better way of saying that a picture is worth 1,000 words. This is a picture that actually solves everything for us for this problem. And now we do the math. I0 less than Q. I0 less than Q, we can find P star T, we can find I star T, and I star T increases monotonically to Q as T goes to infinity, as shown in figure 6.4. And certainly lambda is the same as we already derived before for this problem. We just have to substitute the quantities that we have, constant S and everything, Q dot equal to 0, and we got the lambda dot. We got the lambda T as well. Second case is this case, and we can easily see that P star 0 is bigger than equal to 0. All is here, and at I0 equal to this, P star 0 will be exactly equal to 0. We can also show that the P star dot is bigger than equal to 0, which means that if you begin at 0 or bigger than 0, P star will never go below 0 afterwards. So all of that is working, and we can then show that I star T goes to Q monotonically as T goes to infinity. Case 3. Oh, Kusali, please note that I need a little space after the semicolon, after this colon. Okay?
Yes.
Yeah, just
slide
I'll give
27.
Yeah.
Okay.
Yeah, just space. Just make it more than, just make it perfect as much as we can. Okay. So now I0 is bigger than Q minus S my M1 would have a negative value at P0, which is infeasible. So I would have P star of 0 equal to 0, P star of 0 equal to 0. And then by looking at the picture, we can see that the P star T hat is going to be exactly equal to 0. So what we are now saying is that it will be 0 all the way. Oh, why am I not able to do that? It will be all the way 0 up to here. So the P star T hat will exactly be 0. And then it will start increasing. The slope here is exactly going to be minus s of this side and that side. So this function is continuously lambda t. This is of course p star. P star is differentiable, but lambda t will be also the same. Okay, why are we going here? Okay. So what we need to do is, in case 3, we need to figure out what to do for p star less than t hat and what to do for p star bigger than t hat. Okay. So we already kind of got you all the argument here. You notice that for t less than t hat, I star t hat is exactly this quantity because that quantity is exactly by the curve. I star is the inventory, is depleting, and at t hat, we want the inventory to be exactly q minus s by m1. So you see that's going on here. And we also know that for t less than hat, I star t is I0 minus s times t because it's the slope of s is p star is p is 0, so it's going to be like this. And the adjoint equation in the interval is given by lambda dot of our rho lambda this, and the lambda t hat is exactly minus cp hat. You see here, lambda t hat will be exactly minus cp hat because p star of t hat is 0. So we already have the boundary condition of lambda. So what we can do is we can solve the lambda equation from 0 to t hat by finding the inventory I star of t during that interval. Okay? And we put that interval and put lambda t hat of cp hat, and we are done for the 0 t hat part. So we have the lambda and 0 t hat part. Okay? So we can easily obtain t hat. We already know that. And so complete the solution for I0 bigger than this. For I0 bigger than this, we need two-part solution. We need one solution for interval 0 to t hat, and we need another solution for after t hat. So for less than t hat, we already know this. Okay. Do I see a space missing here after comma? And here's an extra space before comma. Here's an extra space before comma. He has no space after comma. Can you check those? This Kushali, not
Slide
just
28.
yeah, not just slide 48, 28,
20.
but you might want to go over how the slides look and see other places where such things happen. Okay.
Okay.
Yeah. Let's not talk about this in a recorded lecture for every time. Okay, so here's the situation of t bigger than t hat, and I can also tell you that I made another typo that is going to be corrected here as well as in the book. So for t bigger than t hat, we replace I0 by this. So notice what we're trying to do now? We're trying to bring that solution by moving that solution to this point by a transformation t, by changing t, by changing in that solution t by t minus t hat. So that's what I'm trying to do. So for t bigger than t hat, we already have this, and 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 we replace I0 by this and t by t minus t hat on the right hand side of 6.40 and 6.41. So we have this equation already, and we can then find the solution here by I0, because remember this equation is good. This is the same equation here, so we can find the 6.40 and 6.41. and 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 substitute, sorry, substitute for t minus t hat, so we get p star t like this and I star t like this. Then lambda t, I made a mistake here. This is not good. What you do is you go to 6.40 equation, and where is the lambda t? Lambda t is going to be equation like this. It's the lambda t is not here. Where is the, just a second. What did I do here? Yeah, I have lambda t equation is the equation like this equation. So the lambda dot equation. I have to put I star t here. So I star t is this quantity. So I have to substitute I star t here. So you can see now, uh, you can leave that as minus h if you want, and this will remain a plus. But I will change it to so that this equation is easier to read from here. So what I'm going to do is rho lambda plus, so make this correction. So I'm now giving you the correction here, okay? So this equation will be lambda dot equal to rho lambda plus, I did in my book, so let me just go back here. So it'll be rho lambda, this will be plus h, okay, plus h. This will become q minus s by m1 e to the m1 t minus t hat. So replace this quantity by q minus that quantity, okay? And then replace this plus by minus. So it's minus I hat. If you want to keep this as minus, then you have to do the other way. So you have to do minus q plus this plus I hat. So either way is fine, but I'm just going to use plus h now in order, because if I'm going to make change anyway, I might as well be a little bit more consistent with this one. So then it's plus h, substitute this for I star t, and this will become minus I hat because this is minus I hat, because this became plus. Remember, this was a minus here, so so you have to change the sign of this quantity as well. So you get the sign plus sign. So that formula also has to be changed in the book as well as here. So you got it? I can send that to you later to verify, okay? Okay. So, and then we have lambda t hat to minus cp hat, and that can be solved. This is easy to solve. I didn't give a solution, but that can be solved to find lambda t. Because it's a linear differential equation, and then it'll come to be so I didn't solve it, but it can be solved. Okay. Any questions so far? So what we have done is come up with the HMMS model, solve that with optimal control, got some ideas about a turnpike and long-run stationary equilibrium, which is same as turnpike. Now, let me tell you why the turnpike is called turnpike. So suppose this is my turnpike. Think this to be, in Texas, now the freeways have become turnpike. The turnpike is a freeway where you have to pay money. Okay, it's a toll freeway. Toll freeway is called Turnpike, and you will see one of the earliest freeway in the United States was Pennsylvania Turnpike, and that goes from it certainly goes from Pittsburgh all the way to Philadelphia, and so it's a turnpike. Now notice what happens. Generally speaking, if you are so think of kind of finite horizon. And think of finite horizon and think of a problem in which you can actually reach the turnpike in some time. And then you can follow the turnpike. This doesn't happen in this particular case because it's asymptotic, but in many cases it happens, and we'll see that in chapter 7 immediately when we do the next chapter, which will be next, after the exam. Okay, so think about, draw a line here and think about, this is your house, and this is the turnpike, and this is your friend's house, and let's say yeah. So what do you do? How do you go from your house to your friend's house? If you're on the turnpike, which hardly anybody lives on the turnpike, ride on the turnpike, then you don't have to do anything. You just go along the turnpike. That is the case when you live right on the turnpike. But if you don't live right on turnpike, then you'll take a service road and go to turnpike. And then you follow the turnpike, and then your friend doesn't live on the turnpike. So at some point you have to take the exit, and you exit, you go to turnpike. So of course, if your friend lives at infinity, then you don't have to exit the turnpike. You just enter the turnpike and you stay at turnpike forever. Okay? Which means no salvage value, no nothing. Okay? So that's sort of the idea of turnpike. So that's why it's called turnpike. Okay? We'll see more about this later on in chapter 7. And I also wrote some paper in which I try to do something which I may excuse me. I'll talk about that when I get to what is called the Seti Skiba point, which is only briefly touched in the book, but most of it is in the appendix. And that's where you may not be able to follow the turnpike. If you don't follow the turnpike, then you just follow the service road. That's kind of the idea, which is not in the economics literature, and I try to articulate that in one of the papers that I wrote, and I'll talk more about that later. Let me just introduce the problem, and then we'll take a break, or let's take the smallest part of it, the simplest part of it, solve that, and then take a break. The first part of that is exactly what E.G. Thompson wrote in Accounting Review, and I will cover that very quickly. And the second part of this is done by me, which I told you never got published. No, I didn't say never got published. I never published it, but I wrote it in a book, and it's sitting in a book, so I didn't think there was any need to publish it anymore. Okay, so T is the horizon time. XT is the cash balance in dollars at time T. YT is the wheat balance in bushels at time T. VT is the rate of purchase of wheat in bushels per unit time. Negative purchase means a sale. PT is the forecast. It is the forecast of price of wheat in dollars per bushel at time. This forecast is deterministic because we are doing deterministic control right now. And the idea is buy low, sell high kind of idea here. We want to optimize our profit. And so we will show that that is what happens. And R is the constant positive rate earned on the cash balance. And HY is the cost of holding. That means I buy something, then I hold it until I want to sell it, because I want to wait until the price goes up and I sell it. Okay, so but I must incur cost. So that's the inventory problem as well. So it's an inventory problem. It's also cash balance problem. It's also part of inventory literature, and that's why it's in this chapter. Cash. Well, I earn interest, so Rx. And well, I pay money for my inventory holding costs, so I pay minus HY. And since I am buying wheat, V positive means I buy, V negative means I sell. When I buy wheat, I have to pay minus PT times VT. So that's minus PV, so that goes out of my cash. And I have initial cash balance of X0. As I buy wheat, my bushel balance goes up. If I sell, this is negative, so my bushel goes down, and our initial balance of bushel is Y0. I have a control constraints. I cannot buy at a rate bigger than this, and I cannot sell at a rate bigger than this. So those are the constraints on control. And the objective function is simple in this case. I want to I want to maximize my profit, but it is same as maximize my wealth at capital T. So and my wealth at capital T consists of cash plus the wealth tied up in the in wheat. And the price of wheat at time T is PT, and a bushel is YT. So the total value of the wealth, total value of the wheat in my portfolio is this. So my total wealth is this. So I want to maximize this. This is then a Meyer form of the problem. It's a linear Meyer form of the problem. Let's solve this problem quickly, and then we'll go to the constraint part, state constraints later. Hamiltonian is lambda 1 times this plus lambda 2 times v. Adjoint equation lambda 1 dot is minus lambda 1 r, lambda 1 t equal to 1, lambda 2 dot, and lambda 2 is pt. These conditions come from Meyer form, which are these coefficients of xt and yt. And we have this idea here. We can solve lambda 1 dot easily, which is e to the rt minus t. This is very similar to the cash balance problem in chapter 5. And lambda 2t is, there's a h prime yt here, so this integral can come here. Without knowing h, I cannot solve this problem, but I can at least write the formula for lambda 2t, which is given by this. Once I have a lambda 2, I have a bang-bang solution because this is linear in v and a u, linear in v. So the bang-bang solution is minus v2, v1, and this quantity. Okay, this quantity comes from the Hamiltonian part, which is this right here. So if you put that part here, you can get that part there. And if that's positive, I buy as much as possible. If that's negative, I sell as much as possible. Let's take a quick example here. HY is the absolute value of Y, which means I pay the commission either way, now inventory is symmetric. When inventory is positive, I pay holding cost. When it's negative, I pay backlog cost. R equal to 0. To simplify problem, x0 equal to 10, y0 equal to 0, v1, v2 equal to 1, t equal to 6. And I have a price forecast, which is like this. Up to 3 it is 3, and after 4 it is 6. So the price forecast is basically this. Price of forecast is 3, and then at 3 it jumps to 4. And so under these conditions, what should I do? Well, so for r equal to 0, lambda 1 t equal to 1 for all t, because r equal to 0, this r equal to 0 right here. So this lambda 1 t is 1 for all t. And from 6.53, which is this equation, no, the 6.54. This for 6.5. Yeah, lambda 1 t is for 6.3. So that the 2-point binary value problem is x dot equal to, so what I'm doing basically is I'm writing x dot equation. So I put r equal to 0 here, hy is half y. And so I can substitute lambda 1 in there. So I can find the conditions for lambda 2 dot as well. So x dot is this, y dot is given by this, and lambda 2 dot is given by this. So what's going on is that if I take a derivative, this is not differentiable. But we can, given that it's going to be only at one point in time, we can kind of don't want to go into a fancy theory of non-differentiable maximum principle. We can just use our own maximum principle for this case because it's going to just happen at one point. That means the lambda 2 dot, if you solve this, as long as yt is, okay, so what happens is when y is 0, this is not defined. So when y is 0, we have a singular control, and we can easily deal with that with our current maximum principle. And when y is either positive, this means 1, and when it's negative, it means -1. So this is well defined. Only at 0 is not defined. But when it's 0 is not defined, you will see that we are in singular control, and singular control allows us to to find the lambda 2 by equating this. So lambda 2 will be exactly equal to lambda 1 times p. So we can obtain the lambda 2 using this formula. And so we can then assume whatever sign that has to be here to give us that formula. Okay, that's easy to do. It will turn out that this sign will be 0 in that case. So the V star is minus 1, 1 lambda 2 minus p. Since PT is increasing, we know that there is no short selling optimal. Short selling is not optimal. We don't sell now and buy later, which is at price 4. We don't sell at 3 and buy at 4. Since the storage cost is half per unit time, and wheat's price jumps on by 1 unit at equal to 3, it is clear that it never pays to store wheat for more than 2 units of time, because I will only gain $1 for each unit of wheat. And if I store 1 unit of wheat for 2 periods, it will cost me $1. So there's no point for me hoarding the wheat for more than 2 periods. This is important. This is a very important information in solving the problem. So that means that because we have no wheat in the beginning, now look at this, what's going on. We have no wheat in the beginning, and I cannot store wheat more than 2 periods, which means that from 0 to 1, I cannot buy anything. There's no reason for me to buy anything because I will sell only starting at 3, and if I sell starting at 3, buying here means I have to pay extra hoarding cost. This will eat up $1. I only make $1. So if I start buying wheat here and keep it until here, it costs me more money than what I gain. So clearly no reason to buy before 1. Okay. Right. So that's one part. And so we can start buying here at the rate, and the rate of the maximum rate, we can buy here, and we can buy at the rate 1. So we see what's going on here. Since I'm buying at T star bigger than 1, the rate of buying is 1, and we can continue to buy until T equal to 3 and no longer. In order not to lose money on a storage wheat, it must be sold within 2 units of time. So what we're trying to say is that if I buy wheat, sorry. Oh, here's a picture here. Oh, just a second, here's a picture here. Yeah. So if I buy wheat, um, what am I doing here? Let me see. Yeah. So we start buying at T star still bigger than 1, but we don't know when we're going to begin. Okay. That's what we're trying to do here. And whatever we buy must be sold within 2 units of time of its purchase. Okay. That's the idea here as well. So in order to do that, we can say clearly we should start selling the wheat at T3 plus. If you buy maximum rate at 1, we have to start selling at some time 3 or later. So we can continue the last sale time to be T double star. So let's start buying at T star and sell at double T star. If we do that, then in order to sell exactly all of the wheat purchased, we must have 3 minus T star equal to T double star minus 3. Okay, because there is no point keeping the wheat. Once we have it, we should sell it. Once we sell it, there's no reason to keep more than, I should get rid of all the wheat, because if I don't get it, I'm only losing holding cost, and the value of the wheat will stay still at 4 per unit. So there's no reason to keep the wheat once so I must, whatever I buy, I must sell. That's what I'm trying to say. So in order to say exactly all the wheat purchased, we must have this. And during this period, so that means that from T double star to 6, I should not, I should have no wheat, and I should have V star T equal to 0, which is a singular control. And if I have that policy, then I know that YT is going to be strictly bigger than 0. That means I will have a wheat in this interval. Okay. But in that interval, I will have a wheat. Then lambda 2 dot, because I will have a wheat, this is exactly sine of y is 1, because this is absolute value of y, so sine of y will be 1. And half minus half times 1 is 1, half times 1 is half, so lambda 2 dot is exactly half. So in the interval T star double T star, my lambda 2 dot should be exactly half. Okay? And so if it is exactly half, and we know that at T double star, I have a V star T equal to 0. That's a singular control. For singular control, I have to have lambda 2 equal to lambda 1 times P. So at that point, lambda 1 is 0, so I have to have a lambda 2 equal to P. I have to have equal to price. Price is 4. So I would have to have lambda 2 exactly equal to 4 in that interval, because it's singular control. I'm not doing anything. So my lambda 2 has to stay at 4. In order to have a singular control in 0 T star, we must have a lambda 2 T equal to 3. So I should have lambda 2 star minus lambda 2 star equal to 1, because it has to change. Lambda has to change from 3 to 4 from T star when it goes from T star to double T star. So that means that quantity has to be equal to 1, which with lambda 2 equal to half means that T star minus T star has to be equal to 2. And with that equation and that equation, we have to see that T star equal to 2 and T star equal to 4. So if you see all that, our problem is solved. So now what we can see, forget this because we can do the picture. So now we can see that we kept lambda is 0 here. We kept lambda not 0. We kept lambda equal to 3 here. We kept lambda equal to 4 here. Lambda increased by value by slope of half. It went from 3 to 4 in that interval. Because lambda here is bigger than a price, the lambda here is bigger than a price in this interval, I buy. Because lambda here is smaller than the price, I sell. And because lambda 2 is equal, I do nothing. So that's our control. That's our lambda. What is the inventory? Well, the inventory stays 0 because I begin with 0. And then I buy the wheat at rate of half. So at the rate of half, from 2 to 3, I will have an inventory unit, 1 unit of inventory by at time 3. Then at time 3, it says sell. So I will start selling at the rate 1. And by at 4, I would have sold all of that unit by 4. And once I sold all the unit by 4, I will stay there. I mean, this is simple. You can see what is the optimal solution is by inspection if you think about it. But we argued that using optimal control, and we argue that using optimal control, and we come up with that solution. Okay? So that's where Ejiri and Thompson finish. And what I believe is more important to do that, because this is standard optimal control on a simple problem. Accounting people did not know any control theory, so accounting review was happy to publish that paper in long day, long time ago. But certainly that paper would not be published at this point in time. When it's new, it's new. You get a benefit of being new. So now what I'm going to do is I'm going to complicate the problem. The first thing I'm going to do is I'm not going to allow short selling, which means that I'm going to have a constraint on V. We cannot be negative. Okay, so we no what I'm saying, y has to be bigger than equal to 0. That means short selling, y has to be bigger than equal to 0. I cannot have a negative amount of wheat. That's what it means by short selling. I sell what I don't have. Okay, so y has to be bigger than equal. That's a state constraint. So we will look for the state constraint and we'll see that it gives a very interesting solution. And later on, we will give you another constraint on the warehouse, and we'll see that it'll give you what is called the planning and forecast horizons. So at this point, I'm going to break for about 10 minutes, and we'll come back. Is that okay? Okay.